Welcome to your podcast for Lesson 27, Newton's Second Law. After watching the podcast, you should be able to explain how an object's mass and the net force acting on it relates to its acceleration. For class tomorrow, I would like you to be able to discuss the warm-up with the people in your group. So think about whether it's harder to accelerate a bowling ball or a tennis ball, and why. Newton's second law tells us that if you have a force that's acting on an object, a net force that is not zero, that object will accelerate. So it will speed up, slow down, or change directions. And what we know is that the direction of that acceleration is always going to be in the same direction of the net force. If you think about that, that makes sense. If I would sit you on a chair that had wheels on it and I pushed you, you would move in the direction that I applied that net force. The more net force that's applied to an object, the more it would want to accelerate. So if I just give you a little push, you're not going to accelerate as much as if I put a larger force on you in that chair. Okay? Also, the more inertia, and remember inertia is just a measure of mass, but the more inertia that an object has, the more it will resist accelerating. So larger objects are going to require a much larger net force to get them in motion. Right? I think Newton's first law, if an object is at rest, it wants to stay at rest unless it's acted on by another force. Or if that object is moving, it wants to continue moving in that same manner, so at a constant speed in a straight line until it's acted on by another force. So more massive objects are going to have more inertia and therefore more resistance to a change in their motion. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on that object and inversely proportional to the mass of the object. Mathematically, we can represent that with the following two equations. Acceleration is equal to F net divided by m, or, rearranged, F net is equal to mass times acceleration. These two formulas can be added to your formula card. In our definition, we see the words directly proportional and inversely proportional. If something is directly proportional, what that means is that it changes in the same direction by the same factor. So in other words, if I double one value, the other value doubles as well. If I cut that value in thirds, the other value is cut in thirds as well. If something is inversely proportional, that means it changes in opposite directions by the same factor. So if I double one value, the other value is going to be cut in half. Or if I cut one value in quarters, the other is going to be multiplied by 4. Okay. Things to remember about Newton's second law that are important concepts that we can prove mathematically by using these two equations. The stronger the net force applied, the bigger the acceleration. So if we look at our first formula here, basically what that's saying is that if I have the same object, okay, so I'm not changing my mass on the bottom, but if I apply a stronger net force, I'm putting a bigger number on top of that equation. So a bigger number on top means that overall your acceleration is going to be bigger. Okay. Also, the more massive an object, the smaller the acceleration. So that would be making this bottom number a lot bigger. Okay. We would be dividing by a bigger number, and therefore, mathematically, we're not surprised that we get a smaller acceleration. Okay. And if you think about that, that should make sense. It would take less force to accelerate a tennis ball, pushing it around the room with a broom, rather than a bowling ball, because the bowling ball obviously has more mass and therefore more inertia. Real world example that you've probably experienced while you're driving, if you've ever been sitting at a red light next to a Mack truck. It takes a lot more force for that Mack truck to get accelerated the same speed that your smaller car or SUV is in. So it's actually Newton's second law that gives us the equation for the force due to gravity, or weight. And so we added this equation to our formula card the other day, where Fw is equal to mass times g. Okay, so mass times gravity. And so if we look at this scenario here, we have a 2 2 kilogram object in free fall, the only force acting on it then is gravity. And so we know, since there's no normal force, the object is going to have a net force which is equal to the force of its weight. The mass of the object, which we stated is 2 kilograms. Okay. We know that here on Earth our value for gravity is 10 meters per second squared. So we can calculate the net force acting on it using Newton's second law. So if we substitute in our values here, 2 kilograms times 10 meters per second squared, and when we solve, that's going to give us an FW of 20. Now remember, we typically don't represent that with kilograms times meters per second squared. We represent that with newtons. Okay, so if you did not add that to your notes the other day, you might want to jot that down now. 1 newton is equal to 1 kilogram times a meter per second squared. So here are some multiple choice questions that I would like you to have the answer for tomorrow in class. Here's the first one. Here's question number 2. And question 3.